Greetings everyone, my name is Sharif Ahmed Kamran. I am a second year computer science PhD student at University of Nevada, Reno. Today I'm going to present our paper called Fundus2Angio, a conditional GAN architecture for generating fluorescein angiography images from retinal fundus photography. Fluorescein angiography combined with retinal funduscopy is used to diagnose retinal degeneration diseases. The process requires the injection of a fluorescent dye which appears in the optic vein within 8 to 12 seconds. And it can stay up to 10 minutes in the blood vessels. Though the procedure is widespread and affordable, there are certain risks involved. Frequent side effects can range from nausea, vomiting, anaphylactic shock, heart attack, and even death. The only alternative to this is optical coherence tomography or OCT. It is a technique which uses low coherence light to understand morphological information of the retinal subspace. But the differential diagnosis is still dependent on expert ophthalmologists. The problem with this technique is that it isn't easily available in developing countries and the device is really expensive. To alleviate this problem, we propose a conditional generative network for synthesizing fluorescein angiography from fundus images. Our architecture consists of 2 generators and 4 multiscale discriminators. The generators can produce fake angiograms by learning structural information from fundus images, whereas the discriminators try to dictate the produced angiogram is fake or real. To better understand the global and local information, we use a coarse and a fine generator with different spatial dimensions. Rather than classifying the whole image, the discriminator predicts each patch from the image as fake or real. Our proposed architecture consists of multiple residual blocks which are used for both global and local feature extraction. The block consists of 2 subblocks, one consisting of reflection padding, convolution, batch norm, and liquid. The other consists of the same successive layers except for convolution we use separable convolution. To visualize what a separable convolution is, we first do depth-wise convolution, followed by a point-wise convolution. Notice that the point-wise convolution is nothing but a 1-by-1 convolution. Separable convolution is computationally efficient and extract depth information far better than regular convolution. For resizing all inputs of the generators and discriminators, we use Lang's filters. The fine generators consist of 1 encoder followed by 3 residual blocks and 1 decoder, whereas the core generator consists of 2 encoders followed by 9 residual blocks and 2 decoders. The core generator outputs a feature vector along with the output image. The feature vector is then element-wise added with an intermediate layer of the fine generator. The discriminators, on the other hand, consist of 3 encoders. The encoders incorporates a convolution layer, batch norm, and liquid layers, whereas the decoder consists of transpose convolution, batch norm, and liquid layers. For training, our generators we use least square GAN loss. For generators, we use reconstruction loss. The generator loss is multiplied by a weight of value of 10 and then added with the LS GAN loss to calculate the adversarial loss of our network. Our goal is to maximize the loss of the discriminators and minimize the loss of the generators. We use the following hyperparameters for training, but the batch size is 4, the number of epochs is 100, initial learning rate is 2e inverse 4, beta 1 is 0.5 and beta 2 is 0.999. We use Atom Optimizer for training all our architectures together. For training, we start by taking a batch of images. Then we unfreeze the discriminator weights and train them for 2 iterations. Following that, we freeze the weights of the discriminators and train the generators on the same batch of images. Lastly, we train the GAN end-to-end and calculate the adversarial loss. After 1 epoch, we plot 3 random test images and save the snapshot weights of the generators. Ultimately, we save the training history and individual loss values in a CSV file for future reference. We use the dataset provided by Hajib et al. For training our networks. It consists of 30 abnormal and 30 normal pairs of retinal fundus and angio images. We pick 70 normal and abnormal images for training. We do random cropping with 512 and 512 resolution. Lastly, we take 50 crops from each images, ending up with 850 images in total. So next we show a qualitative evaluation of our model compared with 2 other image-to-image translation models called Pix2Pix and Pix2Pix HD. In the first, we show the comparison without using any transformation on the images. To show our model's robustness, we apply 3 special transformations, namely blur, sharpening, and noise. The spatial transformations were done to imitate different signal and periodic noise while capturing fundus images. We can see despite these changes, our model's prediction remains stable and vessels are quite distinguishable in this image. Here are also some examples of some transformations. And you can see from these images that Pix2Pix and Pix2Pix HD were really bad at extracting vessel and arteries from the fundus images, whereas our architecture was really good of extracting this information. Next, we apply two radial transformations called pinch and whirl. This kind of transformations imitates squinting or concentrating of the eye while performing the funduscopy. Despite heavy radial shifts, our predictions retain spatial information correctly compared to other two models. We also carry out an experimentation with real experts involved. We provide 40 fake and real angios with 50% split randomly. The experts are then tasked to correctly identify real and fake angios. For this experimentation, 50% would be a random confusion rate, whereas we achieve a confusion rate of 52.5%. For quantitative evaluation, we use Frechet inception distance. This is one of the most used metrics for GAN evaluation. It uses the encoded layers of VGG16, a pre-trained architecture for extracting different shapes, contours, and structural information, and calculates the difference between the corresponding synthesized and original images. For both with and without transformations, our architecture achieves a lower score compared to the other models. It should be mentioned that a lower FID score signifies a better performance. In future, we hope to extend this work by synthesizing other modalities of ophthalmological data. Moreover, we aim to fuse cross-domain information for better image generation and style transfer. Lastly, we would like to apply this technique to improve existing retinal vessel segmentation applications. With this, I conclude my presentation. Thank you.